Today we're going to be talking about circular motion, which is pretty much just an object that is either rotating or revolving about an axis. Rotation is when an object is spinning on an axis that is within itself. For example, a top is a toy that a kid would spin, and its axis is inside it. The Earth spinning, which causes our day and night, is also an example of rotation. Another example is a skater that is twirling. Revolution, in comparison to rotation, is when an object turns or travels around another point, which is called the external axis. The Earth traveling around the sun is an example of revolution, and the sun is the external axis that the Earth is traveling around. Here's the visual representation of a few things that we mentioned. So here we have the Earth that is spinning on itself. This is rotation. Its internal axis is through the North and the South Pole. But it's also experiencing revolution, where it is going around the sun, and this is revolution, and the axis point is external of the Earth. It is in the center of the sun. Another example of rotation is a record player that is spinning its record, and the center point is right there, and we can see that that is an example of rotation. Linear speed is distance that is moved per unit of time, and we know this from our kinematics unit. Tangential speed is another word that we use for linear speed when we are talking about the object's movement, the object's speed along a circular path. It is a straight line that an object would take if it flew off of the circle. For example, here, if we have an object that is going around in a circle, if it were to be let go or released, it would actually travel in this direction. If it was let go a little bit further down, then it would travel in a straight line wherever it was released. And it can be shown here that these are the directions that the object wants to go, but something is pulling it inwards that is keeping it on this trajectory of a circular motion. One thing to note is that speed does increase as the object's distance from the center increases. So as you go further away from the center, your speed will increase, and this is due to the amount of distance that you actually have to cover in order to get from point to point in this picture here. For example, we have points A, B, and C on this disk, on this circle. We have point A, which is the shortest, and we have point B, which is in the middle, and C being the longest. So as you move further away, we said as you move further away from the center, your speed should increase. 1 revolution is 1 second. So the distance covered from in point A would be 1 meter. So let's say we have a circumference of 1 meter. The distance covered for point B would be, let's say, 3 meters, and then the distance from point C to go all the way around 1 revolution would be 7 meters. In order to get the speed, we know that it is distance divided by time, and our time for 1 revolution for all points is 1 second. All we would need to do is divide the distance by the time, and we would get the speed. The speed would then be 1 meter per second for point A, 3 meters per second for point B, and 7 meters per second for point C. As you can see, the further away that you move, the faster your speed. One thing to note with velocity is that even though you could have a constant speed, velocity is a vector. That means that it has magnitude and it has direction. Because you are moving in a circular motion, you are constantly changing your direction. Because you are constantly changing your direction, your velocity is changing, and you are continuously accelerating. What this means is that you may have uniform speed, but it does not mean that your velocity is uniform. A tangent is a line that touches the edge of a point in a circular path. You may be familiar with this from studying tangents while looking at our graphs. A tangent also plays a part in circular motion. this tangent forms a 90-degree angle to the radius of the circle. What you will notice, again, the object is continuously moving in a circular motion, therefore the tangent is always changing. As the object moves around, the radius will always be perpendicular to the tangent. And this is just showing you the direction that the object is traveling due to inertia. Angular displacement, denoted as theta, is an angle that is moved around a circle from its starting position. It is measured in radians, and it is defined as theta equaling the distance over the radius. If you were to solve for the distance, you would have to just multiply the radius times theta. Here's an example. What is the measure in radians of a central angle theta that intercepts an arc of length 4 meters on a circle with radius 10 meters? We're going to use this equation here, which is theta equals the displacement divided by radius. And if you look over at this picture here, we have the S being the 4 meters and the R, or the radius, being 10 meters. So all we need to do is set that up, divide, and we should get an answer of 0.4 radians. Now, you're probably wondering, radians or degrees? And you're probably used to working in degrees. However, there is an alternate measure of angle, which is called the radian, and it's based on the arc of the angle, also denoted as S, which is the distance or the displacement. And notice that with circles, we have the amount of degrees going from 0 all the way around to a full revolution, which is 360. We also, if we did do this in radians, we know that to go all the way around the circle, it would be equivalent to 2 pi. Pi is equivalent to 180 degrees, which is pi radians, equaling 180 degrees. And 2 pi is equaling that of 360 degrees. So it'd be safe to say that 1 degree is equivalent to 1/360th of the way around a circle. We know that the distance equals radius times theta. In other words, if S is equal to the full circumference of a circle, then the angle would be 2 pi radians. To get a little bit more information or a little bit of history, you can go to this YouTube video right down here. Now, when we're trying to convert from degrees to radians, all you have to do is multiply the degrees by pi over 180, and that will give you the amount of radians. For example, if you were to convert 45 degrees to radians, all you would need to do is multiply that by pi over 180, and you would get an answer of pi over 4, to be exact. Or, if you were to put it into decimal form, this would be the approximate. Go ahead and try this one. Convert 60 degrees to radians. You should get an answer of pi over 3, or 1.047 radians. In order to convert from radians to degrees, all you have to do is multiply the radians by 180 degrees divided by pi. For example, if you were to convert 2/3 pi into degrees, all you would need to do, just multiply by 180 divided by pi, cross cancel, divide, and your total should be 120 degrees. Go ahead and try this next one. Convert 3 pi divided by 2 into degrees. You should get an answer of 270 degrees. Angular speed. Angular speed is pretty much the rate of change of angular displacement. It is the distance that is traveled by an object in terms of rotations or revolutions to the amount of time that it took. Angular speed is also known as rotational speed, and it is denoted by omega, which looks like a cursive W. And omega is equivalent to the distance over time. When we're discussing an object that is moving in a circular motion, we know that S is equivalent to theta over t. So this gives us a new equation to work with. The time that an object takes to go around one full circle, one complete revolution, is known as period, and it is denoted as the capital letter T. The equation is that the period, again, the time that it takes to do one full circle, which is 2 pi, and it has to also take into account the angular speed, which is in radians per second, would give us an answer that is measured in seconds. So this is the equation for period. There is a relationship between angular and linear speeds. We know that 2 pi r is the circumference of a circle. We know the time that it takes to go around once is its period. So we can say that speed equals the amount of displacement, which is the circumference, is 2 pi r, over the amount of time it would take to go around that much. So when we rearrange for period, we get 2 pi r over speed. We know that t equals 2 pi divided by omega. When we set these two to equal each other, we cross out the 2 pi and we're left with the speed equaling the angular speed, which is omega, times r, which is the radial distance. Let's go ahead and use this equation to solve for something. A golfer's angular speed is 6.3 radians per second for his swing. He has two drivers, which is this golf club here. This is called a driver. And one of them is 1.9 meters from his axis of rotation, and the other is 1.7 meters from the axis. Find the tangential speed of each driver. Which will hit the ball farther? Go ahead and try to solve this and then start the video back up. Let's solve for the driver that is 1.9 meters. When we put all of our information of 6.3 radians per second into this, and then the radius being 1.9 meters, we get an answer of 11.97 meters per second, or after taking into account significant figures, 12 meters per second. For the 1.7 meter driver, we have a total of 11 meters per second. So, in order to answer B, we just have to look at our data, which will hit the ball farther. The 1.9 meter driver will actually hit the ball farther because the velocity is higher. Frequency is the number of times an object goes around a circle per unit of time. It is usually within the 1 second time period. It is measured in hertz, which is denoted as Hz. You also are probably familiar with megahertz, which is a 10 to the 6th power, or also gigahertz, which is 10 to the 9th power. The relationship between frequency and period is that they are the inverses of each other. The relationship between angular speed and frequency, here we have angular speed and we have the period equaling 1 over the frequency. Here we have the shared t for time. When we put 1 over the frequency into the angular speed, we get a new equation, which is 2 pi over 1 over frequency, which then gives you the angular speed of 2 pi times the frequency. This will come in handy in some of your calculations. Here's an example. A large clock on a building has a minute hand that is 4.2 meters long. Find the angular speed of the minute hand. We know that the minute hand makes one full cycle in 1 hour, and 1 hour is equivalent to 3,600 seconds. When we use the angular speed equation of 2 pi times the frequency, we can solve that, and we get an answer of 0.0018 radians per second. And that is our angular speed of the minute hand. Part B of the same problem asks you to find the angular displacement in time periods from noon to 12:20 and noon to 2:30. For the first one, from noon to 12:20, we know that that's 20 minutes. So we take 20 minutes divided by 60 minutes, and that is 1/3 of a circle, which is 2 pi, a full circle. And we know that the angular displacement then is 2/3 pi radians. To find for noon to 2:30, we know that that's 150 minutes divided by 60 minutes, which gives us 2.5. So 2.5 of a circle times 2 pi equals 5 pi radian. To find the linear speed of the tip of the minute hand, you would just use this equation. Go ahead and try to solve, and then start the video back up. When you solve for the tangential speed, you get 4.2 meters times the angular speed, which we've already found in a previous part of the problem, at being 0.00175 radians per second, giving us a speed of 0.00733 meters per second. When we take into account significant figures, we get 0.0073 meters per second. Centripetal force. You've heard of centripetal force, and all it is a force that is directed to a fixed center. The net force is inward. It causes an object to follow a circular path. And remember the right angles that it creates, so the object is traveling at right angles to the force, which is called the centripetal force, which moves towards the center. It is center-seeking. And without the force being present, the object would actually just continue in the way that inertia wants it to move. So the object would be, for example, here at V1, it would want to go this direction. However, the centripetal force pulling it inward continuously changes its direction as it goes around the circle. One thing to note is that you do not want to label a force centripetal force, which is denoted as F sub c. You actually want to label it the force that it actually is, and it is the force that is causing the centripetal force. For example, gravity is a real force that holds the moon in orbit around the Earth. So you would not want to say centripetal force for this force. You would say gravity, which we know to be F sub g or mg. Tension is another real force, and that one is denoted as either F sub t, you sometimes see F sub TENS or tense, or sometimes you might even just see the capital letter T for tension. And this is a force that holds the ball as it orbits around its center. Again, centripetal force is tension in this example. Another example is electrical forces, and this is seen with the electron orbiting around the nucleus. And electrical forces are pulling on the electron, which is keeping the electron orbiting around the central portion of the atom. What we know is that tangential speed equals the radius times the angular speed. What we can do now that we know that is we can rewrite this equation to help solve for centripetal force. This equation is mass times the speed squared divided by the radius of the curvature. And here is the equation. So F sub c, which is in newtons, and remember that newtons are kilograms meters per second squared, and that is equivalent to mass times acceleration. However, because we are talking about circles, we know that from a circle, it is the v squared over r, and that equals the angular speed times the radius, which is what we know v is when it comes to talking about circles. So we just put in the omega times the radius, and we square that, and we keep the radius down below, and then we solve, do some cross-canceling, and we get a new answer of the centripetal force equaling the mass times the angular speed squared times r. One thing to remember is that acceleration is produced when a force acts on a mass. The greater the object's mass, the greater the amount of force is going to be needed in order to accelerate that object and keep that object in circular motion. Here's an example. A ball is moving at 12.6 meters per second on a 1 meter string. How much force do you need to make a 10 kilogram cannonball move in the same circle at the same speed? Go ahead and stop the video and try to solve this before beginning the video again. All right, so here we have all of our points of data that we are given. When we plug this in to our centripetal force equation, we get 1,590 newtons. What that means is that you're going to need about 1,590 newtons of force in order to keep that cannonball in a circular motion. We've talked about centripetal force. There is another phenomena called centrifugal force, and it is an outward force that means center fleeing. It is a force that also causes circular motion. However, it's not a real force. Notice here below that there is a diagram that shows the centripetal force, which is being caused by the tension in this string that is holding this object, that is moving the object around in a circular path. The path of inertia here is seen as the tangent. However, if you've ever been in this situation, which we've all been in, for example, when a car is making a turn, we feel like our body is being pushed outward. We're feeling that centrifugal force. And this force is fictitious. It's actually caused by the inertia of what our molecules want to be doing. It's the path of the inertia that makes us feel like we're being pulled out. And if we were to stop, the centrifugal force would go away. Centripetal force, however, is caused by another force. If centripetal force was not named a centripetal force, there would still be a force, and we would call that tension. Centrifugal force is just a phenomena that we experience because of the inertia our molecules in our body are experiencing. For example, if you were to swing a tin can on a string, and inside, if there was a bug in here, remember that the string is the tension and it causes the circular motion. Without that tension, the can would just move in a straight line, right? If you were a bug in that can, you would get pushed to the outside of the can. And if the circular motion were to stop, then gravity is still there, but there would be no centrifugal forces. All right, that's all for our TNOTES. Please read your textbook. The pages are 245 to 252, and you want to just make sure that you read the nature of science sections, which are very important and very interesting. Also check out the worked examples that they have in your textbook, and feel free to peruse and get more information on the online textbook and do some of the practice problems. Thank you for watching. Have a great day.